World War II changed everything about heating. Not because of new technology, because of what we lost. During the war, fuel was rationed. Electricity was unreliable. Families had to survive with whatever heat they could generate from local materials. The cabins that kept people alive used ancient techniques: thermal mass, central chimneys, earth contact, radiant heat. After the war ended, these techniques should have become standard. Instead, they vanished. Exposed, replaced by furnaces that needed fuel. Replaced by systems that needed service contracts. Replaced by equipment designed to fail every 15 years. This was not progress. This was profit. And 10 forgotten secrets expose exactly how they did it. Number 1. The thermal battery hidden in solid logs. Modern building codes measure insulation using something called R value. This number tells you how well a material resists heat flow. Higher R value means better insulation. At least, that is what the industry wants you to believe. A standard insulated wall in a modern home has an R value around 14. A 6-inch solid log wall has an R value of only 8 or 9. Based on this simple comparison, log walls appear far inferior. But here is what the building codes ignore. Logs do not just resist heat, they store it. The National Institute of Standards and Technology conducted a landmark study comparing log homes to conventional framed homes. The results shocked the engineering community. The log-walled test building performed 45% better for heating than the higher R-value framed building. For cooling, the log building performed 37% better, 45% better with a lower R value. How? The answer is thermal mass. Solid logs act as thermal batteries. During the day, they absorb heat from sunlight, from your wood stove, from your body heat. At night, when temperatures drop, the logs slowly release that stored energy back into your living space. Number 2. The lost art of chinking and daubing. Between every log in a traditional cabin, you will find a gap. These gaps could destroy the home's energy efficiency if left unsealed. Pioneer builders solved this problem with materials they found in nature. Traditional chinking combined clay, lime, sand, and animal hair. Some builders added straw or dried grass. Others used moss directly as the primary insulation. This mixture was pressed into the gaps between logs, creating an airtight seal. The technique sounds primitive. It was anything but. Clay has remarkable thermal properties. It absorbs moisture during humid periods and releases it when the air dries. This naturally regulates humidity inside the cabin. Animal hair added tensile strength, preventing the chinking from cracking as the logs expanded and contracted with temperature changes. Moss, still used in Scandinavian construction today, provides excellent insulation. A thick moss layer between logs can add R2 to R4 to the wall assembly. More importantly, moss breathes. It allows moisture vapor to pass through while blocking air infiltration. Proper traditional chinking eliminated 80% or more of air leakage through log walls. Number 3. Why the chimney belongs in the center. Walk through any suburban neighborhood built after 1950. Notice where the fireplaces are located. Almost universally, you will find them on exterior walls. The chimney rises along the outside of the house. It looks attractive from the street. It is also thermally idiotic. Colonial builders placed their chimneys at the center of the home. This was not aesthetic preference, it was survival engineering. A central chimney serves multiple rooms simultaneously. The massive stone or brick structure absorbs heat from the fire and radiates it in all directions. Rooms on every side of the chimney receive warmth. The chimney continues, releasing stored heat for 12 to 24 hours after the fire dies. Now consider the exterior chimney. Half of that massive thermal mass faces the outdoors. Heat absorbed by the chimney radiates into the cold winter air instead of your living space. Studies suggest exterior chimneys lose 30 to 50% of their heat potential through the outside-facing wall. The Weston, Massachusetts Historical Commission describes colonial architecture this way. Colonial style is the first distinctive housing style in New England. Its massive framework is built around a vast central chimney, which provided fireplaces. Notice the wording, built around the chimney. The chimney was not an afterthought, it was the heart of the home. Everything else radiated outward from this central heating core. Central chimneys also simplified construction. A single, massive chimney with multiple flues could serve a fireplace in every major room. One foundation, one structure. Maximum heating benefit. Number 4. the 90% efficient heater they want you to forget. In Northern Europe, a heating technology emerged around the 1500s that makes modern wood stoves look primitive. The Germans called it Kachelofen. The Russians called it the Russian stove. We call it the masonry heater. A masonry heater weighs between 1,700 pounds and several tons. It stands as a permanent fixture in the home, built from firebrick, soapstone, or specialized refractory concrete, and it operates at approximately 90% efficiency. Compare this to an open fireplace at 10 to 20% efficiency, or a modern wood stove at 60 to 70%. The masonry heater captures nearly all the energy from burning wood. Here is how it works. You load the firebox with a large quantity of dry, seasoned wood. You light it with the air vents wide open. The fire burns hot and fast, typically completing in 1 to 2 hours. Firebox temperatures exceed 1,000 degrees Celsius. At this temperature, something remarkable happens. The smoke itself ignites. This secondary combustion burns the volatile gases that normally escape up the chimney as pollution. But the heat does not enter your room immediately. Instead, the combustion gases flow through a complex maze of channels inside the heater. These channels, called the contraflow system, force the hot gases to travel up, then down, then up again through the massive stone structure. By the time the exhaust reaches the chimney, it has transferred most of its heat into the masonry. Secret number 5. Low ceilings. Pioneer cabins averaged 7 logs high. This translated to ceiling heights of roughly 7 feet. By modern standards, these spaces feel cramped. They were also brilliantly efficient. Heat rises. Everyone knows this, but few people think through the implications for their energy bills. Consider a room measuring 15 feet by 12 feet. With an 8-foot ceiling, you must heat 1,440 cubic feet of air. Lower that ceiling to 7 feet, and the volume drops to 1,260 cubic feet. That is 12.5% less air to heat. But the savings compound beyond simple volume reduction. With low ceilings, warm air stays closer to where people actually live. Standing, sitting, or sleeping, you remain in the warmest layer of air. With cathedral ceilings or 2-story great rooms, the warmest air rises to the ceiling peak, 15 or 20 feet above your head, while cold air settles at floor level where you walk. Modern homeowners install ceiling fans to push warm air back down. This requires additional energy and still creates uncomfortable air currents. Pioneer builders simply kept the ceiling low. The sleeping loft represented another stroke of genius. In a cabin with a sleeping loft, the loft naturally collects the warmest air in the entire structure. Children sleeping in the loft stayed warmest through the coldest nights. Number 6. Using the earth as your furnace. Dig down 4 feet almost anywhere in the continental United States. The soil temperature you find will remain relatively constant year-round. In most regions, this temperature hovers around 50 to 55 degrees Fahrenheit. Think about what this means. In January, when the air temperature drops to 0, the Earth 4 feet down remains at 55 degrees. In August, when the air temperature reaches 100, the Earth 4 feet down remains at 55 degrees. The Earth itself is a massive temperature moderating system. Pioneer builders understood this intuitively. Root cellars maintain temperatures between 32 and 40 degrees year-round, with zero energy input. These underground rooms kept vegetables fresh through winter and cool through summer. The design was simple. Dig down below the frost line. Build walls to hold back the earth. Add minimal ventilation for moisture control. Earth-sheltered homes took this principle further. By building partially or fully into a hillside, or by berming earth against exterior walls, builders dramatically reduced heating and cooling loads. The Department of Energy confirms that earth-sheltered designs can cut energy consumption by 50 to 80% compared to conventional construction. Number 7. The living roof your builder. For centuries, Scandinavian builders covered their roofs with layers of birch bark topped with living sod. These turf roofs appeared on homes, barns, and churches throughout Norway, Sweden, and Iceland. The design was not decorative, it was functional. The birch bark layer served as waterproofing. The flexible bark sheets overlapped like shingles, directing water down and away from the structure below. Birch bark resists rot for decades when protected from direct sunlight. The sod layer above the bark provided remarkable insulation. Depending on thickness, turf roofs achieved R values between 15 and 25. The living grass added additional benefits. The plants absorbed summer sun through evapotranspiration, cooling the roof surface by 10 to 15 degrees. In winter, the sod layer trapped snow, adding another insulating blanket. Perhaps most importantly, turf roofs were fireproof from above. Sparks landing on a sod roof simply extinguished. This mattered greatly when your neighbor's chimney might throw sparks across the village. The weight of a turf roof also held the entire structure together. Heavy roofs resisted wind uplift and kept the building stable through storms that would strip conventional roofing materials. Modern green roofs on commercial buildings represent a partial return to this ancient wisdom. But residential turf roofs remain nearly unknown in America. Number 8. The strategic placement of every window. Walk through a pioneer cabin and count the windows. You will typically find one or two. They face south. They are small. This was not poverty. This was physics. Glass transmits heat rapidly. Even modern triple-pane windows achieve R values of only 3 to 5. Compare this to a solid log wall at R 8 or higher. Every square foot of window loses 3 to 5 times more heat than an equivalent square foot of wall. Pioneer builders minimized window area to minimize heat loss. But they did not eliminate windows entirely. They placed them strategically. South-facing windows capture solar heat during winter months, when the sun tracks low across the southern sky. Properly sized roof overhangs then shade those same windows during summer, when the sun rises high overhead. This is passive solar design. It requires no equipment, no electricity, no moving parts. It simply requires understanding where the sun rises and sets throughout the year. Northern walls in traditional cabins often had no windows at all. No sunlight enters from the north. Any window on the north wall represents pure heat loss with no solar gain to offset it. Number 9. The airlock your front door needs. Open your front door on a winter day. Feel that blast of cold air rush into your home. Watch the warm air from inside billow out in a visible cloud of condensation. You have just lost a significant portion of the heat your furnace worked to produce. Traditional builders solved this problem with the vestibule. A vestibule creates an airlock between the exterior and your living space. You open the outer door and step into a small, intermediate room. You close the outer door. Only then do you open the inner door to enter the main house. The cold air stays trapped in the vestibule. It mixes with the small amount of warm air in that buffer space, tempering somewhat before you open the second door. Meanwhile, the warm air from your living space never directly contacts the frigid outdoors. Studies suggest properly designed vestibules reduce cold air infiltration by 30 to 50% compared to a single exterior door. In Alaska, these buffer zones are called Arctic entries. They are considered essential features in cold climate construction. The Inuit developed an even more effective design called the cold trap entrance. The entrance tunnel sloped downward, then back upward before reaching the interior. Cold air, being denser than warm air, settled in the low point of the tunnel and could not rise into the living space. Colonial homes featured keeping rooms near entries, partially serving this buffer function. European manor houses and castles routinely included vestibules. Number 10. The difference between warming air and warming people. Modern forced air heating systems work by heating air. A furnace or heat pump warms air in a central location. Blowers push that warmed air through ducts to registers throughout the house. The warm air rises from the registers, mixes with room air, and eventually warms the objects and people in the space. This approach has fundamental problems. Warm air rises. It stratifies, with the hottest air collecting at ceiling level while cooler air sinks to floor level. Your head may feel warm while your feet feel cold. Moving air feels cooler than still air. The very act of blowing heated air creates a wind chill effect that makes the room feel cooler than the thermostat indicates. Forced air systems circulate dust, allergens, and pathogens throughout the building. Every time the blower activates, particles become airborne. Radiant heating works differently. Radiant systems heat objects directly, not air. Like sunlight warming your face, radiant heat travels in waves and is absorbed by solid surfaces, including your body. The air temperature can remain relatively low while you feel perfectly warm. The Romans perfected radiant floor heating over 2,000 years ago. Their hypocaust systems circulated hot combustion gases through channels beneath raised stone floors. The stone absorbed heat from the gases and radiated warmth upward into the living space. These systems operated at remarkable efficiencies, with floor temperatures reaching 77 to 95 degrees Fahrenheit. Korean ondol systems worked similarly, routing hot smoke from cooking fires through underfloor channels before exhausting out a chimney. 10 secrets. 10 techniques our ancestors understood and applied. 10 approaches the modern building industry has systematically abandoned. Thermal mass, traditional ceiling, central heat sources, masonry heaters, low ceilings, earth contact, living roofs, strategic windows, airlock entries, radiant warmth. None of these concepts are lost. The knowledge exists. The research confirms their effectiveness. The techniques can be applied today, but they threaten established industries. Builders prefer standardized methods that maximize square footage and minimize construction time. Material suppliers prefer products with built-in obsolescence. Energy companies prefer customers who consume maximum fuel and electricity. HVAC contractors prefer systems requiring annual service contracts. The construction and energy industries have spent decades conditioning us to believe that comfort requires complexity. That warmth demands technology. That staying cozy means staying connected to the grid. Our ancestors knew better. In 1943, that elderly couple in their grandfather's cabin stayed warm through the blizzard without a furnace, without ductwork, without a monthly energy bill. Their cabin incorporated thermal mass, central chimney placement, strategic window orientation, likely an airlock entry, possibly even earth berming against the north wall. These features cost nothing to operate. They required no fuel delivery. They did not fail when power lines went down. The cabin was built to keep people warm, not to keep industries profitable.